Excellent. So next we're gonna talk about the COVID-19 classification algorithm that we developed specifically to analyze the data from this Luminex assay and the data generated from the assay. Again, I always just put the recap because if you do look at the slides at another time, I just want you to have all the links there. So I'll just click through this quickly. Today, we're going to talk about the development of the algorithm, the samples that were used to train the algorithm, and also the performance. And I'll also give you an introduction to the algorithm itself that I hope is not too complex, but gives you enough information to be able to interpret and understand the algorithm that we're applying to the data. So first of all, why do we need a classification algorithm? As you know, the multi-antigen SARS-CoV-2 panel that we developed was developed, first of all, for research purposes. So we're not, this isn't a diagnosis tool or a diagnostic. It's a serological tool that allows us to detect and identify individuals that had past exposure to SARS-CoV-2. And the nice thing is that we don't need to have the knowledge of previous exposure. So for example, people who go get a PCR test because they're symptomatic, that's very specifically getting a test because they're feeling ill. Whereas with our assay, we can just collect, as Dr. Maria went through in the first sessions, we can do cross-sectional surveys of different communities, and we can collect samples from individuals, that may or may not be having symptoms, and get a sense for the extent of transmission in a community. We've also multiplexed several antigens. So there's both SARS-CoV-2 antigens and then other viral antigens. So we're measuring the presence of IgG antibodies to all of these antigens at the same time. And so this gives us a lot of information about this person's antibody profile. And importantly, the antibody measurements to all of these antigens, that they're best interpreted together instead of just looking at them individually. And so in order to do this, we need advanced statistical methods that can consider this combined, what we call, or what many people call, a serological signature. And the signature, because our antibody panel, our antigen panel includes both SARS-CoV-2 and also other viral antigens, we get this whole, holistic serological signature that considers presence or absence of antibodies to all of these different antigens. So machine learning algorithms, such as random forest algorithms, can be trained to predict exposure and to robustly classify samples as recently exposed or not recently exposed to SARS-CoV-2. I think we lost someone. Tama, are you guys still there?
Maria dropped out, but it's all right. We're continuing from mine.
Okay. And importantly, this random forest algorithm can also learn what this serological signature to other viruses looks like. And so then we can also avoid misclassification of samples from individuals that may have been exposed to other viruses. And so potentially they do have, they do have an immune response or an active immune response, but it's not specific to SARS-CoV-2. And so they're not misclassified as recently exposed when actually they were exposed to maybe influenza or another seasonal coronavirus. So I'm going to give you a bit of a background of what the random forest machine learning algorithm is. I just included a little joke because I feel like this topic is quite heavy. I'm going to start with a simple example. And Tama, this is where I was like, oh, perfect. I'm going to use you as an example because we do what a random forest machine learning algorithm does every day, all the time. And that's when we make decisions. And when we make informed decisions, we have to consider all the different possibilities, use our prior knowledge to kind of inform how we make those decisions. So for example, how do you decide which mode of transport you will take to work? So I've just given an example. Your thought process might be, okay, well, if I walk to work, it will take me exactly 30 minutes. I've done it before. I know the route. I know the pace that I walk, so it'll take me 30 minutes. If I take the bus, I could get there in 15 minutes. However, if the bus is late, I won't make it in time because it might take 45 minutes or an hour. And so then if the bus is late, maybe it's best for me to take a taxi. And then I know that I'll be there in 10 minutes. But then if there's traffic, and then that's kind of how you make these decision trees. And we do this all the time to make complex decisions at different points of our lives. So I hope we haven't lost everyone, but I was wondering if any of you can think of some examples of decision trees from your own life, or maybe what that process might look like for you. Oh, sorry, I see a comment from Val. Sorry. And I'll address this before we get to the example. So Val's question is, can the assay also measure SARS-CoV-2 IgA and IgM? Yes, it can. I think at the moment it's been established for IgG, which is why I specified that in this talk. But we have used it to measure different classes of IgG. And I should also note, oh, hello? Did anyone have a question? Okay. And then in order to include IgA and IgM, we may or may not have to retrain the algorithm. And if antibodies to IgA antibodies or IgM antibodies become important features to classify samples as positive or negative, then we can retrain the algorithm by giving it both IgG, IgA, IgM, or potentially IgG is the biggest signal, and then we can still measure IgA and IgM and apply the same algorithm that we have now. I hope that was clear, but if you have any follow-up questions.
I was just wondering, I know I've missed the last session and kind of missed part of the first session as well, so I'm way behind, so apologies if this is already mentioned beforehand. But does this assay, can it distinguish between those that have past exposure to SARS-CoV-2 and those that have been vaccinated? Did you hear that? Sorry.
We lost you a little bit, but I think your question was, can this assay detect exposure from infection versus vaccination? Was that the question?
Correct.
Yeah. Yes. And Fee, I'm glad you're here because you probably might want to jump in. But from my understanding, we can, because we have different antigens for the SARS-CoV-2, we have the ability to look at vaccination, anti-spike immunity versus potentially antibodies to the other antigens that would be most likely from natural infection. Is that correct?
Yeah, and one of the main antigens that allows that distinction is the nuclear protein, which is why we decided on having that in the panel. And so the combination of antigens in the panel have specifically been selected to help us differentiate between natural infections versus vaccine-induced immunity.
Okay, thanks.
Yeah, and I should mention that, now that we do have so much more, I guess the situation in PNG is different in terms of vaccination rates, but we, at the moment, the algorithm has only been trained, and I'll get into this, on samples that were, naturally exposed to SARS-CoV-2. So, we may want to consider also training an algorithm that is trained on naturally exposed versus vaccine induced immunity. So that will definitely be something I think to consider in the future.
Thanks.
And Val, did I answer your question? Or did you have any follow-up questions?
No, you answered it.
Great. So back to the decision tree. Does anyone want to give an example of maybe a decision tree and the process of how you might come to a decision of anything? Doesn't have to be super complex. It could just be like, what am I having for breakfast?
I'll offer one. Mine is always, do I get myself ready first and then my child, or get my child ready and sit him down and then get myself ready? And it's often about what's going to be the least tantrumy or least, the quickest way to get out of the house.
Yeah, great example. So, Fee might be thinking, well, in the last 2 days, I took 10 minutes to get ready, and then it took me 30 minutes to get Teddy up and running. So given that, maybe today I'll start with myself. And so that's kind of how, we do this on a daily basis. Any other examples?
Ours was which computer would connect to the camera so we could join this session, and which one was the fastest. Yeah, we've tried different laptops and different connections, and we even had our phones on standby.
Yeah, exactly. So now, like, if you were to train someone, now look, I recommend you use this laptop with this connector, with this.
If someone else takes it, go fight for that laptop and bring it. Yeah.
Great example.
Shazia,
Yes.
mine kind of my decision tree this morning was a bit of what Fiona's had and the example you gave. So I had to decide if I got my baby ready and left him at home first, like would I make it in time for the workshop? And then I figured that out. And then we also had to decide which route we take to get to to this building. So yeah, we took the unsafe route, but we got here faster.
Yeah, informed decisions. Great examples. Anyone else?
I was just going to say mine was actually this morning, which route do I take to work? There's only 2 ways, but one way the road is much worse than the other way, but then the other way the traffic is not so great.
Yeah.
Do I go through the route that's got a really bad road, or do I risk it and deal with the traffic the other side? So that was my decision-making process, which route to take to work this morning.
Yeah, great examples. So the reason I wanted you to think of these kinds of examples is that that's exactly what this random forest algorithm is doing. The nice thing is that it builds these decision trees, and each decision tree is independent of the others. So we can run this, iteration or this kind of training thousands and thousands of times and get almost like a probability of what may be the best option. And every time you go down that decision tree, you might get a different result. So for example, maybe Tama or Becca today said, oh, I'm going to take this road because I know that today there isn't traffic. But then tomorrow there might be traffic, so you might actually take the other one. And so it kind of helps you, it basically is trained in the same way that we make our own informed decisions. Tama, did you want to say something? I can see you're unmuted. Oh, all right. So that's kind of a simple example. In the case of our data, the algorithm is using the information from every single antigen to kind of come up with a prediction. So looking, I think I had one more example that's a bit more computational, I guess. So I hope you can see this tree. I might actually move the videos over here so I can see it So let's say we want to train this random forest algorithm to be able to classify these ones and zeros into the 3 different groups that I can see that there are. So we have blue zeros, we have red zeros, and we have red ones. So there's 2 features that that the algorithm can use to start to tease apart these groups. One of them is color, and the other one is whether it's underlined. So how does the algorithm go through this? So if we start with just these ones and zeros, the first question we can ask, is it red? So if it's not red, then we've correctly classified all of the blue zeros. However, if we said yes, we still have 2 different groups or classes here. We still have underlined ones and red zeros. So then the next question we need to ask, is it underlined? And if the answer is no, then we've correctly classified the red zeros. If the answer is yes, then we've correctly classified the ones. So this is kind of what the algorithm is going to be doing with our data. And it's gonna have the information for all 11 antigens. And it will say, okay, is there a presence of antibodies to S1? Yes. Okay, then maybe it's SARS-CoV-2, but are there also antibodies to influenza? Yes. Then what does that look like? And that's kind of how it's using the information from all of the antigens to come up with whether a sample is from a person who was recently exposed, so sort of positive, or negative, not exposed. Any questions at this stage? All right, move the videos back so I can see you. And like I mentioned before, what the random forest algorithm does is it builds thousands of these decision trees. And for each decision tree, we get 1 final prediction. So in this case, we've run 9 decision trees, and there's been 6 predictions of a 1. So let's just say that this is positive and negative. So 1 being positive. We have 6 votes or 6 predictions for a positive result or a positive prediction, and 3 zeros. So because the 1 was outvoted, then the final prediction is yes, this is positive. So that's kind of how the algorithm is working in the background. We run thousands of decision trees to train the algorithm, and then we get a prediction of what that sample is most likely to either be positive or negative. And I'll talk about the sensitivity and specificity, or the performance of our classifiers in the next few slides. Is that making somewhat sense to everybody? If you can put a thumbs up if it's all right, or if you want more discussion. Excellent. Wonderful. So now I'll go into the details of our classification algorithm. I think I've kind of already said some of these before, but the features from all of the 11 antigens are used, or were used, to train the random forest algorithm. And so instead of having sort of color and underline like we did in the previous example, we have presence and absence of, antibodies compared to negative samples. And then also the level of IgG. So we know that, antibody data is not binary. It's not just that you have and you don't have. You can have antibodies, but you can have low levels of antibodies, you can have high levels of antibodies. So all of those features are considered by the algorithm to determine whether a sample is positive or negative. We've trained the algorithm using samples that we know have been exposed to SARS-CoV-2. So we actually tell the algorithm, it's like in the previous example with the colors, we actually tell the algorithm, these are the blue zeros. And so then it uses the classifying features and the different questions to say, okay, how can I actually classify these blue zeros correctly? And how many times did I classify them correctly when you run all of those decision trees? And that's how you get your performance indicators. So we had data from samples that we knew had been exposed, so from people who had recovered from infections. And we also had many samples that were not exposed to SARS-CoV-2 so that the algorithm can learn what a positive sample antibody profile looks like and what a negative sample antibody profile looks like. And then the results, as I alluded to before, is a prediction of either seropositive or seronegative, with positive meaning that that person was recently exposed to SARS-CoV-2 and negative not recently exposed. And this prediction becomes, is a result of all of those thousands of decision trees, so the ensemble of decision trees. So just a bit more details on the actual samples that, or data sets that we use to train the algorithm. The positive samples came from 4 independent Melbourne studies. And they're from WeHi, from University of Melbourne, from the Doherty Institute. And then these samples for the PNG algorithm included samples from the COVID profile study, which is the study that we're leading from Evo's lab and in collaboration with Leanne and others. So that's why I've just put a bit of a star. And I know, Tama, you asked this question in one of the previous sessions. In the app, you will see that there's PNG algorithm and Melbourne algorithm. The difference between these is that for the PNG algorithm, we included COVID profile study samples, because we know that in PNG, there's no way that that's going to be a confounder. However, in Melbourne, because the team here also uses the app, we train the algorithm also by excluding the COVID profile samples so that they could use the Melbourne algorithm to determine positivity in the unknown COVID profile samples. And so that's why for your purposes, you'll always be using the PNG algorithm. And then for the negative samples, we had we had several sort of pre-pandemic controls. So this would be, obviously before we even knew SARS-CoV-2 existed, so that we're completely certain that there's no confounders of antibodies to SARS-CoV-2 in these samples. And these samples came from some of the Melbourne studies, such as the Doherty Institute study. We also had samples from blood donors from the Australian Red Cross from 2019, I think 2019, and also from the Volunteer Blood Donor Registry at WeHi. So these were all samples that we were sure were negative. We also had a few samples that were possibly cross-reactive. So these samples were negative to infection with SARS-CoV-2, but they were possibly people who had been infected with for other seasonal human coronaviruses, possibly influenza, etc. So then that also trains the algorithm of what a person who might be exposed to a virus would look like. So yes, they have presence of antibodies, but to which antigens? And that's where it will learn how to kind of distinguish between a SARS-CoV-2 positive sample and negative sample. So the antigens in the panel, and I know we've gone through this already, but I thought I would just remind you, we have 5. So the purple antigens are the 5 SARS-CoV-2. So back to the question before of vaccine versus natural infection, the spike antigen is the one we would expect to have high levels of antibodies in the case of vaccination, also possibly also with natural infection. But if we do have, in particular, high levels of the NP or the nucleocapsid protein, then we could begin to distinguish also between natural infection and vaccination. We've also included an influenza antigen, a tetanus toxoid positive control, and then several other human coronaviruses or seasonal coronaviruses that we know circulate as well. So that's just a bit of a reminder so that you can think about how the algorithm is being trained. And then in terms of how we actually, so Beck's got a question. Because the algorithm is trained for antigens, not only for SARS-CoV-2, will the results from this assay tell us this also? For example, positive for influenza. Great question. So I think it's actually a complicated question, because I think in theory, you could potentially determine that someone has had exposure to influenza, but the algorithm hasn't been trained with samples that were positive for influenza. So that kind of beginning information that we've given it to learn how to determine positivity has been based on SARS-CoV-2 positivity. So we would have to rethink the way we train the algorithm. But I mean, with the data we're collecting, it gives us a marker, but it's not a comprehensive influenza panel of antigens either. So it's probably not the best for those purposes because it wasn't designed for that purpose. But yeah, Fee, I don't know if you want to add anything now that you're here.
No, I think you're exactly right. In terms of determining seropositivity, the algorithm would need to be retrained with known positive influenza samples. However, when you do get your readout, you can tell an individual that has higher readings for influenza, which you would assume is that they've been exposed to influenza, whether it was more recently or in the past, but we can't definitively say that they're positive or not.
Does that answer your question, Beck?
Yes, thank you.
Excellent. Thanks for the question. So just to finalize the nitty-gritty of the algorithm, and I don't really expect you to know all of this, but I thought it was great for you to just get an overview of how the algorithm is actually trained, so that it makes more sense when you're interpreting your data. So before we train the random forest, we divide the data set into sort of 3 stratifications or 3 categories. And the reason we did this was because we do know that antibodies to SARS-CoV-2 do wane. We know that they wane after a certain period of time. And we had the ability with the positive samples that we had in our data set, we had a range of days post-symptom onset. So the median was 54 days, or about 2 months, but we also had up to 185 days. So we could kind of go up to the 6-month mark. But we know that someone who's been exposed 5 months ago will probably have lower levels of antibodies than someone who was exposed 2 weeks ago or 2 months ago. And so we wanted to make sure that we took this into consideration when we trained the algorithm with the positive samples. And so we've actually trained 3 separate classifiers. The first one is just everything. So all of the positives and all of the negative samples in the data set. And so we don't differentiate between time since symptom onset. For the second classifier, we do all of the negative controls, and we restrict it to the positive samples that were more than 2 weeks post-symptom onset, but up to 3 months. So more of that acute phase, if you will, or maybe that's not the right word, but more recently exposed. And then the third classifier was included the data set with all of the negative controls and the positive samples with symptom onset between 3 and 6 months. So sort of that later stage. And then for each classifier, the way you train the algorithm is you give it the data set, so those 3 data sets, and then 2/3 of the data randomly is used for training. And then the remaining 1/3 of the data set is used for validation. And I don't really, we don't really need to get into that, but all you need to know is that that division of the data set happens randomly. And that's why if you run this classifier different times, it'll choose different random samples of the 2/3 of the data set. And you may get different sensitivity and specificities. So we did do this a few times, and we opted to choose the highest sensitivity and specificity options. And I'll get into that in the next slide. And then the other thing that you need to know is that the built-in algorithm in the Shiny app, it predicts exposure using all 3 classifiers. So you will get 3 predictions of exposure status for each sample. So you'll get, the classifier 1, classifier 2, and classifier 3. And, we will go into that in the next session briefly, but usually we don't have any knowledge of exposure. So you probably want to make an educated guess based on all three. But sometimes you may know that this person, or that there was a wave that happened in this community a month ago. So you know that if anybody would have been exposed, that would have been exposed within the last 3 months. I'm just giving examples. I think these are things that we need to be discussing together as we start processing more samples and start to discuss which classifier may be the best. We have had instances where certain samples are considered positive by one classifier and not the other, and that happens because we know that the sensitivity and specificity is not perfect. And so that's where I think it's worthwhile to have discussions on how to interpret data when we have those specific cases. And then finally, to just tell you about the performance. So on the left, this is a typical curve to show sensitivity and specificity of a classification, or in this case of the classifiers. So you can see on the y-axis is the sensitivity or the true positive rate. So we expect that, X percentage of the time we're getting true positives as a result of our predictions. And then on the x-axis is the specificity. And this is actually 1 minus specificity, I think. And it's the true negative rate. So what percentage of the time are we actually classifying negative samples correctly as negative samples? So that's sort of like the opposite of a false positive rate. And for the three classifiers, we had very high sensitivity and specificity, so over 90% for all of them. And then you can just see how that differs depending on the three classifiers. Really, they're all higher than 90, so we're getting pretty robust results. But I think something to keep in mind is that, the algorithm learns from the data that's it's fed or that it's given. And so, we have used very specific sample sets early on in the pandemic and in the peak in Melbourne to kind of train this algorithm. So, I think we just need to keep that in mind. It's not perfect. And everybody's algorithm is going to be slightly different. This is quite standard. Most people who are doing these kinds of analyses are doing exactly what we're doing with the sample sets they had available. So just to keep that in mind, I think. And yeah, that's it for this session. And the next one is just more practical on how to apply the algorithm to your data set in the app. So I think I've just got the acknowledgements for these sessions and all of the resources there if you want to come back to this. And then I'll just open to any questions or discussions before we take maybe a short break and then go into the practical side of things.
I was just wondering, would the type of vaccine that you've had affect the assay results in terms of distinguishing antibodies between past exposure and those that are vaccinated, or in terms of, antibody levels that are waning? For instance, like after a certain period of time after you've been vaccinated, would the type of vaccine that you've had affect the assay at all? Do you know?
Do you mean the assay or the prediction? Like the assay itself, or?
Yeah, maybe the prediction of yeah.
Yeah, so I think, I should have maybe specified that a bit more in this presentation, but this algorithm was developed with samples from pre-vaccination programs in Australia. So that is something to consider. I think obviously that this was all work that happened, 2020 into last year. So we probably do need to think about how to update the algorithm to consider vaccination. But then that being said, I think even using this one, if you get a positive value, you can then look at those samples in more detail and maybe look at, the antibody levels to the different antigens in more depth. You know, obviously we're getting a positive prediction, but then you can also then look at all of those positive samples and see what the levels of antibodies are to which antigens, and potentially from that information get a sense for, you know, vaccination versus natural infection. But that is an area that we haven't added onto this algorithm at this stage.
Yeah, okay, thanks.
I mean, I think it's something, you know, I've been thinking about that actually while putting together this workshop. We now have lots of samples, even within the COVID profile study, for example, we have a vaccination arm. So we would be able to provide those 3 classes or groups, you know, positive by infection, positive by vaccination, but I don't know the data. I haven't looked at it at all. So I don't know how clean it is, if that makes sense, or if it's already difficult to discern just from the antibody data itself. But yeah, I think it's something we need to consider, possibly an updated version of the algorithm if you have samples that have been collected after, you know, mass vaccination programs, or, you know, areas that have high vaccination rates, for example.
Yeah, okay. Probably doesn't, it's not going to make much difference to PNG at this stage, just due to the vaccination rate being so low, but
yeah, exactly. But yeah, no, it is something to just make sure that you do keep in mind, especially when you're thinking about applying this to different, you know, sample sets or studies. And if there does need to be more explicit consideration about vaccination, to just have those discussions. I think we would be able to update the algorithm. And I'm not sure if that's being thought of here in Melbourne for some of the COVID profile data, but I'm sure we'll be having those discussions soon.
Yeah, okay, thanks very much.
Questions from anybody else? Thumbs up if